Oh, all right then. So I think I'm going to try to make this lecture not too long because it's sort of like off schedule, and because my goal is just to finish this handout, so there's not a lot left. So I hope this will be all right. Okay, so for all of you to sort of like spend a little bit of time completing the things that we have already started in the lecture about electric field. So what I'm going to do today is to sort of like add just a little bit on top of those and finish up the Coulomb's law. Okay, and let's hear me out a little bit here. So what I was sort of like I ended last lecture with the note saying that the things that we are doing right now, the force in the electric field, it's pretty much analogous to the force that is that's a mass is being experienced in a gravitational field. They are pretty much the same. All right. So I always sort of like show you this analogy a couple of times just to confirm that this analogy works so well because it's based on the same idea. So the force under gravitational field comes from the mass in that field multiplied by the strength of the field. That's it. That's the whole concept of the field and the force. So we're going to do the same thing here today is what if you would like to figure out the force that acting on a charge Q that is located inside an electric field. So the amount of force is going to be Q times E, and that's it. It's done. Isn't that cool? So I hope this sort of like make things easy enough in the sense that if you look at this equation, the Q, don't forget, you have two types of charge. It's either positive or negative, right? So the good thing about this one is it's already a vector equation. So what it means is if you are looking at a positive charge inside a field, wherever the field is pointing to, the force will pointing in the same direction as the field in the case of positive charge. And if you have a negatively charged particle, then whatever the field is pointing to, the force will point opposites. That will be opposites. That's it. So this equation works perfectly. Even though in the case of the gravitational field, you always have the mass experience the force in the same direction as the gravitational pull, right, or gravitational fields. But in the electric fields, you have choices now because it depends on what type of charge you put in. If it's a positive charge, okay, so it behaves just like mass in the gravitational field. Wherever the direction of the electric field is pointing to, the force will point in the same direction. However, if you place a negatively charged particle in a field, wherever the E is pointing to, the force vector F will point opposite to the field E. That's it. That's the game that we are going to play. But the rest is simple. Whenever you see a field, you will be able to track the force right away by just using the charge times the field. Let's take a look at a quick example. I'm letting you know that I'm not gonna do this in our class. Not to do this means they have like a big example how to apply this sort of like force and fields and all this stuff, and they incorporate the projectile motion. I think you remember this one. So this scenario try to sort of like give you a perfect comparison with the gravitational field. So let's take a look at this. We're just going to talk about this briefly just so you know how similar these two fields are. So let's take a look at this. If you have an electric field pointing up, okay, so that's the orange arrows, those are electric field pointing up. Then you're shooting in an electron, let's think of it as an electron. So it has a negative charge in it. Then the velocity at first, let's give it like a horizontal direction. So it's going to come in from left to right. But once it's enter the region that has electric field pointing up, so let's focus on, for example, at this point right here, I'm going to just write this on top of one of the field line right there. Because electric field is pointing up, okay, but the charge we are looking at is negative. So this particle is going to experience the force pointing down. You guys with me? Okay, so if the charge of this particle, even though it's an electron, but it can be any negatively charged particle, then it will experience the force of QE magnitude. That's it. That's how simple it is. Okay. And then because you're shooting in horizontally, but you have a force pulling down. So this scenario is exactly when you throw a ball horizontally and it's going to curve down due to the gravitational pull. And that's it. This is going to give you a projectile motion in the exact same way that you analyze the projectile motion in the mass. All right. But I hope my point is just only this. Electric field is pointing up, but the electric force is pointing down due to the negative charge on this charge Q. That's it. Okay. And on the other hand, if you were to bring in like a positive charge and you shoot it in, of course, it's going to curve up. Okay. All right. Because at the point that this charge experiences the field, it will have the force point in the same direction as the field. That's for positive charge. And this for negative charge. All right, that's it. That's my point right here. Okay. And you don't have to worry about whatever charge is moving or not in whatever direction. The only relationship that the force and the field has is just that's it. It's either the same direction as the field or opposite to the field. That's it. Okay. All right. So with that in mind, then we can now arrive at our finally Coulomb's law. Okay, so we had E equal to K, the constant, times the charge generating the field divided by the distance from the source to the point of calculating the field, KQ over R squared. Now, I'm going to do this, and I hope this will clear things up. So if that charge generating the field is sitting right here, let's say is a positive charge. So what you're going to have is going to be, all right, we said last time, around this charge, you always have field pointing out, 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 out. Yeah. All right. And the direction is outward, radially outward like that. Okay. All right. And now if you are sitting right here, electric field, if this is at the distance r away from the source, the electric field at this point is going to be K Q. Let's say Q is the charge of this source over R squared. Clear. All right. So I hope this is done. I can even put the direction of the field at this point here. That's my electric field. And then I can turn this into a vector and say that this is R hat. And the R hat is this direction right here. I think this is good. This is clear. All right. So this is your electric field vector pointing out, radially outward right now. Now, what I want to do is I'm going to place another charge there. So because now we're going to have two charges. So what I'm going to do is I'm just going to call this source to be Q1 right there. Okay. And now I'm placing the next charge, the second charge right here at the location that we know already there is an electric field there. And I'm going to call this charge, I mean, the amount of charge on this one, let me have it like Q2 charge on this. So your question or my question to you is, what is the force acting on the Q2 charge, guys? Well, okay, Adan, now you have the charge, you have the field. So I can say right away, the force acting on this charge is going to be just Q2 times E. And that's it, you're done. You guys with me? Because let's assume that if this Q2 is positive, the force due to this field will point in the same direction. So that is your F right there, the green one. I think I'm using a very bad color at this point. All right. Oh, my bad. Well, let me use black then. Okay, that's a force. There you go. Right, F is right there. It's pointing in the same direction as the field, the red one. Okay. And now I can just write down everything. It's going to be K because we know what the E is. It's going to be Q1 in there. And then you have extra Q2 from the front over R squared. And R hat is still sticking around. No problem. And that's it, guys. That's what you have right here. K Q1 Q2 over R squared. That's exactly what you have right here. And that is our Coulomb's law. Okay, so my way of introducing this Coulomb's law to you through the field first. Once you get the field, you can always be able to calculate the force acting on a charge sitting at that field by just multiply the charge with the field, and then you're done. That's it. That's my take on this. Okay, and now we can officially introduce the K. That's a Coulomb constant. And the number is around, here we go, is like some numbers, but usually we can round it up to about 9 times 10 to the 9th. And the unit, you have to rearrange a little bit. It looks crazy, but that's what it is, Newton meter square per Coulomb square. However, it turns out, you will see this in a couple of lectures ahead of this one, I mean later, this K that we are using right now can be written in terms of another constant that I would say even more is like super fundamental, and that is an epsilon naught. All right, but all right, we'll take care of this epsilon naught a little bit later. But for now, what I want you to just sort of take with it is just, you have two ways of writing the K. If you sort of like, okay, I don't want to write too many things, just write down the K. But if you want to put in like a full crazy looking form, you can put it as 1 over 4 pi epsilon naught. Okay, cool. All right. Another point that I just don't want to just sort of like passing this by. You might be wondering, well, Ajahn, when you place the Q2 charge in this scenario over here, don't Q2 charge has its own fields? You say, yeah, you're right. And if you sort of think about this, that is very good, because we said every charge has its own field. So that means Q2 charge also has its own electric field coming out. Right now, let's assume everything is positive, so we don't have to worry about flipping the directions or anything, but that's what it is. So that means when you place the Q2 charge in this particular setup over here, Q1, that's first being the source of the field for the Q2, will also experience the same, not the same, but I mean, experience the field due to the Q2 as well. So that means we should be able to calculate what force is acting on Q1 based on the fields generated by Q2 as well, right? Let's try that, shall we? Okay, let's stick with the blue, guys. Stick with the blue. So look at this. The Q2 now being the source of the fields at the position of Q1. How big is the field? So let me call this E sub 1 now. I'm sorry, E sub 2. Okay, sorry, just E sub 2, just to distinguish from the E that we already had. So this is the fields from Q2. But you say, Bajan, it's going to be K, the charge from the source, which is Q2, divided by the separation, but it's going to be the same distance, right? It's going to be R squared. But whoa, Bajan, it's exactly the same formula, except you just change Q1 to Q2. That's perfect. That is fine. Now here comes the whole conclusion. What about the force? So you say the force acting on Q1. So let me put F1 now. And then I can put 2 later just to say, hey, this is a force on Q1 due to Q2 if you want. It's going to be the charge that experienced the fields right now is Q1 multiplied by E2. You guys with me?
Okay.
Okay, so far so good. And now I place everything into this equation. It will look like K Q1 Q2 over R squared. Can you notice something here? It's exactly the same as the Coulomb's law that we just wrote. Same value. So these 3 red boxes are exactly the same. And that's good. The reason I'm saying this is good because this is the action reaction. And it's a Newton's third law. We say that every force in this universe has to come in pair. So that means if you know how to calculate the force that Q1 is acting on Q2, then the Q2 will act pretty much the same amount of force on Q1. Okay, and that is conclusion.
Okay.
Wow.
This is the reason why if you look at this formula is, I would say, is symmetric. This is the reason why you have a product between Q1 and Q2, because Q1 will exert some force on Q2, and the Q2 will exert some force on Q1. Same amount, according to Newton's third law. Perfect. Okay. All right, and that's my conclusion. Oh, that's our slide look very bad. Right? It's very dirty. I don't know why. All right, but I hope you sort of like see my intention over here that now we should be able to calculate the magnitude. We should be able to determine the direction. Once you get the magnitude and directions, that's the vector that you want. Okay. And now you can talk about force or you can talk about field. No problem. Okay, cool. So I hope you see where we want to go today. And the action reaction, that's the one that I'm explaining in this slide right here. All right. You can, well, this is sort of like more like a traditional way of writing things down a little bit. Okay. All right. Now, toward the end, of course, in general, in a system that you are considering, you might not have just only two charges acting. You might have like a bunch of charges that you want to sort of like, all right, get together, and then you want to do some net force on some particular charge. But you already did this back in the day of the electric field. All you need is just the vector summations among those vectors. Same thing will happens on the force. Okay, so it means if you would like to figure out the force on particular charge, for example, like charge number one, and then you have like a charge number two, number three, number four, all the way to the end acting on this. All you need to do is just sum all those force due to each pairs. So one acting with the two, one acting with the three, one is acting with the four, or on and on. And then you sum all those vectors. All right, we'll see this in our exercise right now. Okay, here we go. Almost done. So I hope if you guys sort of get this one, then I think, all right, today I try to make it short because I know it's sort of like a Saturday morning and then we probably don't want to deal with this too much. But I hope if I can finish this part about the force and the field, then I'm happy. Okay, in the figure, three charged particles lie on an x-axis. Okay, here we go. Particle 1 and 2 are fixed in place. Particle 3 is free to move, but the net electrostatic force on it from particle 1 and 2 happens to be 0. So it means charge number 3 does not feel anything. It's like net force on it is 0. If the distance L12 and L23 is given to be the same, they want to know what is the ratio of the charge on Q1 and Q2. Oh, this is cool. All right, so let's start like take a look at this one first. Because they don't tell you what type of charge Q1 and Q2s are, you probably have to come up with some idea what's supposed to happen. Because Q3 experienced 0 net force. So let's assume. If Q3 is positive first, let's assume, okay? So that means Q1 and Q2 must give force on Q3 in the opposite direction. So you're free to assign anything as long as you are able to make the net force on Q3 to be 0, right? For example, if I set Q1 to be positive, the force due to Q1 acting on Q3 is going to point in this direction. You guys with me? All right, so let me take these examples just to make sure that you get everything that we already introduced last time. All right, start with the field. Q1 will generate a field pointing out in all directions. I'm not going to draw too much now, but everyone should be able to imagine this in your head. And because we assume that Q1 is positive, so the field is pointing outward. Good. So at the point of Q3 location, electric field is pointing outward. That's why. Let me name this E1 right there. Cool. All right, I can put a vector on it too. There you go. And now, because Q3 is positive, so let me draw this vector over here. So the force acting on Q3, force acting on Q3 due to the charge number 1. So let me write it as Q31. Sounds good? It's going to point to your right because positive charge will experience the force in the same direction as the field. And that's it. That's why I can always write force 31, F31 to be to the right away. But this coincides with what you already understood. Q1 is positive. Let me highlight a little bit. Q1 is positive. Oh, sorry. Q1 is positive. Q3 is positive. Positive charge will repel each other. Makes sense. Perfect. So that's perfect.
Okay.
So you have positive charge nearby, they will repel each other. So because you are focusing on the charge number three, so that's no doubt the force acting on charge number three will point to the right, away from charge number one. But if you are analyzing charge number one, you will experience the force point to your left because they're gonna have to repel each other. Does that make sense to you? Okay. All right.
Okay.
Try again. So let's do charge number two. So the charge number two, it's going to act with the charge number three as well. But then because you want the net force to be zero, so you probably can guess the charge number two should have an opposite sign. So you should have a negative sign in the charge number two. And when the number two charge is negative, you are placing next to the charge number three that is positive. They're going to attract each other. Now, once you're focusing on the charge number three will experience the attractive force right there. F acting on number three due to the charge number two. Let me write it as F32. Perfect. That's good. Okay. All right. Sounds like fun. All right. But anyway, you can always come up with a different sign, but as long as you have the different charge on Q1 and Q2, you are able to get the zero net force on charge number three. That's the only requirement that you need. All right. All in all, for these problems, all you need to do is just comparing the size of the magnitude. So what you want is just you want the magnitude of F32 to be the same magnitude as the F31. You want them to cancel. Okay. And now we will be able to calculate the force between each pair. Let's start from the left. Between 3 and 2, you used to do K, Q3, Q2 over the separation between the two. So it's going to be L23 squared. Cool. On the right is the F between 3 and 1. So it's going to be K, Q3, Q1 over L13. But then L13 is twice as big because they said L12 and L23 are exactly the same. So it means the distance from charge number one and charge number three is going to be twice the L23. And then you take this square. Almost done, guys. Q3 cancel. Can you see that? Okay, let's pause right here. Once I cancel the Q3, do you see what is going on here? Can you see? Once I slash out that Q3, or actually let's eliminate that. What do you see? Well, Ajahn, it's a KQ2 over L23 square on the left. This is the electric field right here due to the charge number two. With me? Okay, let me name this E2. So that's E2 right there. And when you look on the right, KQ1 over 2L23 square. Well, this is the E that generated by Q1 at this point. So let me name this E1. So this is sort of like go in circle and just want to confirm that you can compare the force acting on the charge number three, or this problem is exactly the same of saying that the net electric field at the position of the charge number three is zero. Or that means the electric field has to be exactly the same as well. Okay, you see what I'm saying here? So you have, I mean, because the force and the field are super connected, so when the force is zero, it must mean that the field has to be zero as well. So that's mean if the net force is zero at the position of the charge number three, the net field at that point must be zero as well. Okay, so you have sort of like two ways that you can arrive to the conclusion. It depends on what you want. But eventually, during the process of getting to your answers, I mean, it's already revealed that, all right, it's the cancellation of the field. You can do that too. Okay, so back to our business over here. Now I can slash K out as well. Okay, and L23 already gone. Just left with the factor 2 in there. And that's it. That gave you the conclusion over here that Q2 is going to be Q1 over 4. And that's conclusion. The ratio of Q1 over Q2 is going to be 4 times. And that makes perfect sense because Q1 is further away from Q3. So if you want to have an ability to cancel out the field from Q2, which is closer, you need the magnitude of the charge to be bigger to compensate for the distance that is further away. Okay, sounds good?
Okay.
All right, and that's done for this. So I hope it's not too bad in terms of setting up the either you're gonna say it's the Coulomb's law or you want to say it's just the electric field calculation. They are pretty much the same. Okay, and sometimes in some problems, if they are not asking you to figure out the force, you might be able to just deal with the field if you want to. Okay, let's take a look at the next one. For example, over here, you have 3-point charges are arranged as shown in the figure below. Find the vector force on the 5 nanocoulomb charge. The nano is 10 to the negative 9. All right, but that's just a prefix right there. Okay, guys. So you want to find the vector, the net force on the charge number 5, which is at the origin in the coordinates right here. So this is where I would like to, I hope I can draw a nice diagram for you guys. So you have 2 ways of doing this. Okay. One way, you start with the field first. Okay. I'm going to show you that. And I hope by solving these problems for you, then I think it's going to be clear how it's done. So I'm going to approach this problem using my way of doing is starting with the fields. When I'm starting with the fields means what I'm going to do first is I'm going to just forget about this 5 nanocoulomb charge for a while. Okay. Just forget about it at this point. So I'm going to just ask you guys to, hey, what is the field at the origin? Just figure out the field at the origin first. Okay, let's try that one. So let's start with that. So I'm going to just name this one number 1 then so we can have like a subscript that looks nice. And we're going to name this charge to be number 2. Okay, first, let's zoom in a bit. The charge number 1 is negative. The negative will generate electric field point towards it. Okay, so now your source is negative. So that means your electric field will point towards it. With me, guys? Very good. Now for the charge number 2, it's a positive charge. So the fields will pointing away from it. Pointing away from it. So at the origin, you will feel that the electric field will point away from it. So I hope by just writing these 2 arrows is enough now. You don't need that electric field lines coming out of it anymore, right? I hope. All right. All right. Okay. So that's it. Because now you have only 2 charges generating the fields at the origin. That's all you need to figure out. So I can name this too. All right. The first one, let me name this E1 electric field. And the other one is going to be E2 electric field. Okay. Now, because you know the directions already, what's left for you to calculate is the magnitude. So what is the size of the E1 magnitude? You say, is it going to be K? The charge generating the field, 3 nanocoulomb, or let me write it as like 10 to the negative 9 coulomb over there, divided by the separation. Okay, right there. They said is 1.1 meter away from the origin. So I can put 0.1 meters square. That's it. That's the magnitude of my E1. Okay, cool. I'll keep going. Figure out the E2, the E sub 2 electric field due to the charge number 2, that's 6 nanocoulomb is going to be K. The charge that is the source of the field divided by the distance from the source to the point of consideration is 0.3. And then you square this distance. Very good. All right, so now you get the size of E1, you get the size of E2, you know the directions. What is going to be your net electric field, guys? Mo Adan, you can do it. by using Pythagorean theorem. That's going to be your net electric field, the green one. That is your sigma E. There you go. And the size of the sigma E can be calculated using Pythagorean theorem. So it's going to be the E1 square plus E2 square, the whole thing under square roots. Yes? Very nice. And that's it, in the sense that that's your net electric field. All right. I don't think we need to put some numbers in there, but I think you can sort of punch the calculators, get the final answer and everything. That's good. And then look at this. This problem actually just only asks you to figure out the vector though. Here, find the vector force. So actually these steps, I don't think we need it. No need, because these steps will give you the magnitude, right? But because this problem, they just want a vector already, which is good. The blue is already in the y direction. The red is already in the x direction. So let's leave it there. Let's jump right into the final conclusion. So what I'm going to do is, how can we figure out the force, guys? To get to the force, I bring back the charge, the one that we forget about it in the first place. It's just like I place back that 5 nanocoulomb charge at the origin. So I will have to say, okay, John, my sigma F, the net force, is going to be 5 nanocoulomb charge multiplied by sigma E vector at the point of the origin. You guys with me? Simple. Force is charge times E times field. That's it. And what I can do is just say it's 5 nanocoulomb. See, I can start with the red because the red is already in the x direction. So I'm going to plug it in here. Here we go. I'm going to say E2 negative I hat. You guys with me? Because E2 is point to your left. So I'm just going to use unit vector that's showing that is pointing to your left. And then I say plus that I have another component pointing along the y direction. It's going to be E1, but now E1 is pointing down. So I can say this one is negative j direction. And that's it, guys. I can just answer this. Be done with.
Okay.
It's like, okay, because I didn't want to do the numerical calculations and everything, but that's what it is. As long as you just want to get to the vector force, you don't need to do Pythagorean theorem because they are not asking you to figure out the magnitude. You can just leave it as is because one is already pointing in the x direction, the other one is pointing in the y direction. So you can use the ij notation to represent your final vector. However, if they are asking you to figure out the net force magnitude, it's easy too, because if you want the magnitude of the net force, you just take that charge 5 nanocoulomb and then multiply by the magnitude of the field at that point as well. Which, I mean, of course, that you need to do that Pythagorean theorem. However, this exercise just showcase how simple it is to get from the E to the F. Just take the charge and multiply the fields at that point. Sounds good?
Okay.
Right. But for those of you that were done, I did no, it looks good and all, but I still prefer doing the Coulomb's law. I want to figure out the force from each pair. I would like to do that. So you can do the same thing over here. So let's take a look at this. So let's look at the black ink over here. So if you say, I don't want to sort of take away my 5 nanocoulomb in the first step, I just want to leave the system as is and just want to do the calculation right away, you can do that too. So look at this. So if you want to start looking at the net force on the 5 nanocoulomb charge, you look at, okay, I have the charge number 1, the blue. The 5 nanocoulomb is positive. The blue is negative 3. So they are opposite charge. They are going to attract each other. So that 5 nanocoulomb charge will experience the attractive force pulling down. How much? It's going to be K, Q1, 5 nanocoulomb, Q2, 3 nanocoulomb divided by the separation square. There you go. Now you look for the other force acting on this 5 nanocoulomb charge. There's a 6 nanocoulomb charge over there. They are positive, so they're going to repel each other. So look at the 5 nanocoulomb charge. It will experience the force pointing to your left because it's going to be a repulsive force. So there's going to be a repulsive force pointing there. There you go. Okay, then the magnitude of this force is going to be K, Q1, Q2, 5 nanocoulomb, 6 nanocoulomb, divided by the separation between the two square, 0.3 square. And you start seeing that it's exactly the same thing. Okay, it's just having the common factor of 5 nanocoulomb here. But if you're looking at just the field over here, you just don't have that 5 nanocoulomb charge at this moment, but it will come in later. So it's just like, it depends on you want to deal with the field first and then get to the force, or you just say, hey, I just want to deal with the force right away. But at the end, you get the same answer. Okay, sounds good?
Okay.
Right, so this kind of shows us a couple of times, and then just pick your preference. Okay, if you want to go with the field and follow by the force, or you just want to jump ahead and just calculate the force directly, both way are equally good methods of solving problems. Okay, sounds good. All right, my personal preference is just get the field first. That's all. That's why
Okay.
I introduce sort of like the field, and then everything just come after that. Okay, I hope you get the feeling of what is about to happen. I mean, there's nothing much to it anymore. So let's try one more. It's get more complicated here, but I think this is gonna be like a grand conclusion. Okay, so why don't we? Okay, here's the news. I'm debating with myself about how far I'm gonna go today, and because the rest of this one is gonna be calculus. If you're not gonna like it so much, why don't we take this to be our final exercise for today's lecture? Sounds like a good plan. Okay, and then I think we can attack the calculus together when we have like a lot more people in class, and then some. I mean, you might have questions on and stuff, and then for those of you that had a chance to look at this force and field, then we have a couple of days to revise the whole thing first before we attack the same problem, but it's a calculus based problem. The complication is not the physics. The complication is mathematics. All right. So let's take this one as the not calculus. All right, it's a simple one. I'm just gonna show you how it's done. The question in the exam will be straightforward. I'm gonna give you a super like a big hint, a super clue that you'll have a chance to solve that problem quite straightforwardly. So don't worry, it's not gonna be like super complicated. But I think it seems that I cannot just not mentioning this calculus based problem. I think it's kind of like, wow, well, it's college, it's university of physics, so we need it somehow. All right, so let's finalize today's lecture with these problems, guys. Okay, take a look at this one and see what are you going to start this problem with. In the figure, you have particles. Now it's getting more and more particles in the figure now. You have Q1, Q2 given the amount of charge on there, Q3, Q4 as well. And the distance is also given. The A is 5 centimeter. They want to know the X and Y components of the net force on particle 3. Okay, they want to get the net force. And because they want the X and Y components, so that's a good thing, that it means you just do your vector decomposition into the horizontal and vertical direction and just leave it there as your final answer. So that's good. All right, but anyway, this is going to be more complicated now. You have sort of like 4 particles in here. You want to know what is going on with the particle number 3. All right, so let's approach this one just like what we did first with the field. Okay, and then we attack the force at the end. Okay, let's do that. So first, if I want to do that, I'm just going to have to forget about charge number 3 for now. So I'm just going to let me eliminate this first. Okay, let's forget about this charge for now. Let's say pretend that it's not there. So what I'm going to have to figure out is the net electric field at the location of charge number 3. Sounds good? Okay. So let me mark the sign correctly. Q1 is positive 100. So that's positive 1. Q2 is negative 100. Or actually, I can just put the charge on there. Just make it easier to reference. There you go. And Q3, it's 200 that we're going to place it later. And Q4 is negative 200 nanocoulomb. Okay, cool. All right, let's get started. Start from the charge number 1. It's a positive charge, so electric field will coming out from it, and at the position of, we can name its origin, right? Because charge number 3 is sitting at the origin. So the electric field at the origin due to the charge number 1 will be, let me use the red one, is gonna point downward. With me? Okay, very good. Now I'm just gonna need a little bit of like sort of like that. There you go. All right. So now we'll move on to the charge number 2. Number 2 is negative. Charge number 2 is negative. So the electric field will point towards it. So it's going to go like this. Yes. Cool. Now, charge number 4 is also negative. And it looks like it's pretty strong. It's like, it's like, wow, its charge is 200 and stay pretty close. So let me draw this a little bit big, longer arrow right there. But it's going to point towards the charge number 4. So this is it, guys. These 3 arrows or vectors are those net electric fields. So all you need to do is just sum these 3 vectors together. You're going to get the net electric fields at the origin. Okay, sounds good. So let me name this one E1. Let me name that E2 according to the charge generating the field. And let me name this E4. There you go. All right, now we know all the directions. All we need is just the magnitude. So let's start from the magnitude of the E1. There you go. All right, E1 is going to be K. The charge that's generating the field, let me put 100 nanocoulomb right away, divided by the distance from the charge to the location of the calculation is going to be A. So let me put A for now. So make it a little bit cleaner. All right, but you can substitute A to be like 0.05 meter later. But that's E1 right there. It's done. Pointing down. So if you want to specify right away it's pointing down, you can just, okay, it just depends on how you would like to write your, whoa, this is way too big. Yeah, it just depends on how you would like to draw this one. Write this one down. All right, if you want to write it as a vector, so it will look something like this. Or I think, why don't we just put on the side? Okay, here we go. Or I can say E1 vector is going to be the magnitude, and it's going to be negative J. Okay, you guys, is it better? Yeah?
Okay.
Okay, all right. Now you got the magnitude. You look at the arrow, it's pointing down. You can write the vector for the E1 to be the magnitude and minus J pointing down. Okay, now try the E2. E2, same thing, K. The charge that is generating the field, and it's going to be Q2, and Q2 is also 100 nanometer. I'm sorry, 100 nanocoulomb. Now divided by the separation from the charge generating the field and the point of calculation, it's going to be this diagonal over here. So the distance over there is going to be A root 2 from the current theorem. Okay. All right. So that's no problem. It's going to be A root 2 squared. So if you would like to represent this one as a vector, now it's going to be a little bit tougher because it's sort of diagonal, right? But don't worry, because you can split this into 2 components at all time. So what I can do is, because eventually we're going to break it into X and Y components anyway. So what I can do is just going to break this into E2 in the X component. This is going to be E2 cosine 45. If you want, if you want to call this 45, but 45 is 45. Sine or cosine doesn't matter. And then you have this E2 sine 45 in the horizontal axis. All right, so that means I can split this and write it as E2 magnitude cosine 45, and that is the I hat because it's pointing in the positive x direction. With me? Plus E2 sine 45, and that is up, is the J. Isn't that cool? All right, so two's down. Now three, the third one, the blue, I want the magnitude of the E4. E4 is already horizontal, which is good. K, the charge that's generating the field, which is 200 nanocoulomb, over the separation, the distance from the charge to the location of calculation is going to be A squared. Yeah, good. And because this one is already pointing in the positive x direction, I can actually write the vector for this one to be the magnitude and I hat. Almost done.
Okay.
Here comes the final step. This is your net electric field, guys. Okay. What is the sum of these? Sigma E. Just take these three and add together. But then because you want the components, right? I mean, because you want an x and y, you want to write everything in terms of vector, this expression will come in handy now. Okay. And then you start from the x-axis first, the I components. So look at this. So let me put everything into a combination for the I. You can see that I have E2 cosine 45. Let me put it like root 2 over 2. Okay. That's from here, right there. Okay. Let me highlight for you guys. Okay. Let me write it down first and I'll highlight for you. So the first component is coming from the I components from the E2, and the blue, the E4. Perfect. That is in the I direction. With me, guys? So this is good. So let me highlight this. That's here. And this comes right here. There you go. That is a horizontal part. And then you move on to the vertical components. Plus. Okay, now you collect all the J. You have the up J, E2, sine 45. And then the red is pointing down. The red is pointing down. So you have a negative E1. There you go. And everything is in the J hat direction. With me? Okay, let me highlight for you. So the E2 root 2 over 2 comes from here. That is your up component of the E2. And the rest is this. E1 right there is pointing down. Okay, so I hope this clear up all the components that you have at the origin. Okay, got that one? All right, so this is the electric field at the origin. Now, final steps is going to be super easy. You bring back the charge that you eliminated in the first step. There you go. Saw that one? Okay. There you go. Bring back. Okay. Now I just place back Q3 at the origin. But because you have already known that at that point, the sigma E is already given up there, I can just say the force, total net force on the charge number 3 must be equal to just the Q3 multiplied by the sigma E that you just got up there. And that's it, you're done. Woohoo!
Okay. Okay.
Like that. See, that's how simple it is. I mean, you just have to go slowly, components by component. I mean, actually, you can think of it as like each charge will generate the field. And then you take the field from each charge, collect them, and then do the summation to get to the net field. Once you get to the net field, Then, yeah, place a charge there. That charge will experience a force equal to its own charge multiplied by the field at that point. Think of it like mg. You have the mass in the field, the weight is mg. You have the charge in the field, the force is QE. Same thing. Okay. And I hope you can exercise this if you want to approach differently. I mean, if you want to use like a Coulomb's law, the force between pairs of charge, then you can try this, go through this problem one more time, and then consider a pair of charge instead. For example, you will have to start with this. It's going to be the charge, the force between Q3 and Q1. That will get one pair of force. I mean, one pair of force, right? Because force come in pair, but that's what it is. So you get the force that acting on Q3 due to Q1. And then you have to consider another pair. There you go. I write it like a chain or something like that. That Q3 is interacting with the Q number two. And then you have to look at Q3 acting with the Q4. So if you would like to use the Coulomb's law, then you have to consider one pair at a time, collect the force, another pair, collect another force, another pair, collect another force. But at the end, you're going to get total like 3 force vector that you need to do the summation that looks exactly just like this, except there will be Q3 built in into each terms. So it's going to come down to the final same answer. But if you approach through the fields, Q3 will just popping up toward the end. But if you want to do in terms of the Coulomb's law, because the Q3 is there with you all the time, you have to consider each pair that is pairing up with the Q3. You're going to have Q3 all in your, I mean, in every sentence or in every line of your calculations. That's all. Okay, but at least the final answer will look exactly the same. Okay, sounds good? I think this is pretty good. All right, so I hope you get the connections between the field and the force, and calculus is coming to you later. All right, and that's, I think this is it for today. I think this is enough for sort of like get the final conclusion about the force and the Coulomb's law. Okay, sounds like a plan. All right, and then we'll see each other again on Monday, and then we'll attack the calculus based problem together. Okay, all right, this is not too much, I hope. All right, thank you for stopping by, guys. I know it's Saturday morning. Is I don't think physics is appropriate. All right, have a nice day. Thank you. Yeah, you too, guys. Take care. Bye bye.